We turn now to the theory of acid-base reactions, and this has a very interesting history because, as we mentioned before, Arrhenius, in his PhD work, began studying the conduction of electricity in salt solutions. And this fascinating aspect, in which he placed different salts into water and measured the conductivity, led him to realize that when an acid was placed into water, it produced ions that contribute to the conduction of electricity through these systems. And his studies revealed that the nature of ions that resulted from the dissociation of salt into cations and anions carried directly over into an understanding of acid-base chemistry. And the theories regarding acid-base chemistry then emerged from his recognition that H3O plus, or H plus without the union to water, was the cation that was responsible for changing the conductivity when an acid was placed into a liquid. And as I mentioned before, this was part of his PhD thesis, which was rejected by his PhD committee, and that didn't slow Arrhenius down, and it's a very good lesson for all of us. So his PhD thesis began to define a very important factor, and that is that an acid dissolves in water to produce H+. And we are writing this as H3O+, because quite often we are reacting water with the acid, and that H+ actually bonds immediately to its neighbor H2O to form H3O+. But more than that, he said a base dissolves in water to produce the hydroxide anion. So this is the first generation of theories of acid-base reactions. Now, as the understanding blossomed in acid-base chemistry, Bronsted-Lowry came up with a somewhat different definition, and that is that an acid is a proton donor. That's an extremely important thing to remember, that an acid donates a proton, and of course when we look at H3O+ that's formed by putting an acid into water, that acid has donated that extra H to form that H3O+. But in stark contrast, a base is a proton acceptor. Now, acceptor is a gentle term for what actually happens. What actually happens is when the base is put into water, it steals a proton, because that base has a greater ability to draw hydrogen off of water than does water to draw hydrogen off of the inserted base. So that distinction is very important. And in fact, this second generation of acid-base theory forms the most common way of analyzing acid-base reactions. Now, the third generation of acid-base understanding came from G.N. Lewis, who was, as we know, so important to thermodynamics, and in his formulation, an acid is an electron pair acceptor. And we'll see how this works. And in the same vein, a base is an electron pair donor. So we move from the Arrhenius view, where an acid dissolves in water to produce an H+, to Bronsted-Lowry that says an acid is better interpreted as a proton donor, and the reciprocal definition of a base is a proton acceptor. And we'll see how this balance works when we look at reactions. And finally, the Lewis approach, where an acid is an electron pair acceptor, a base is an electron pair donor, and as we know, Lewis always focused on the electrons. So let's turn to this view of Arrhenius, where all acids release H+ in water. And whenever we look at an acid-base reaction, we always come back to sketch in our minds what the structure of water looks like with its highly electronegative oxygen and its relatively electropositive hydrogen atoms, which gives this very large delocalization of electron density toward the oxygen. So let's take HCl, one of the most famous strong acids, and let's react it with water and see what happens. The formation of the product H3O plus leaves us with the anion, the chloride anion, as the other product. And in this case, K equilibrium is very large. That means, of course, that there's a large release of Gibbs free energy in this reaction, and it also means that the reaction shifts profoundly to the products. And so we actually write this with a single arrow, not as an equilibrium, because the reaction goes to completion. So every HCl that goes in, virtually everyone, produces an H3O plus. And that, as we will see, is a definition of a strong acid. Now let's look at what happens. We have a Cl atom bonded to a hydrogen atom, and the collision with water, which has a couple of hydrogen atoms and an oxygen, results in the interaction of the bonding structure of HCl with water. And what happens then is that the negative and the oxygen end of water successfully steals that hydrogen atom from HCl, leaving the free chlorine anion and forming our H3O plus, which is composed of 3 hydrogen atoms bound into oxygen. And we have the positive charge resulting from the transfer of that H plus, that proton. That was, in fact, the view that Arrhenius put forward, defining what an acid is. But now let's look at the base case. For the base, let's take a very famous example, ammonia. And as we know, ammonia is extremely important globally because it's the primary agent that fertilizes crops. It's the fertilizer that was developed as we turn to the 20th century, and the result of forming NH3 by the Haber process is what exploded the productivity of crops worldwide and supports the population growth. So let's take ammonia and let's react it with water, which is exactly what happens in the soil, and that forms NH4 plus and OH minus. In that particular process, and it's strongly shifted to the right, but will indicate that equilibrium. But now we come back to our fundamental relationship between H3O plus and the hydroxide anion, namely H3O plus, the concentration thereof, times the hydroxide concentration is equal to our K water, our equilibrium constant for water, which we also know is equal to 1 times 10 to the minus 14 at 298 Kelvin. Well, we can calculate the H3O plus concentration as soon as we know what the concentration of the hydroxide anion is, because we simply multiply the equilibrium constant for water times 1 over the hydroxide anion concentration, and we can calculate H3O plus immediately. So let's investigate at a molecular level what happens in this reaction. We start out with NH3, which is nitrogen, 3 hydrogens, and we react that with water, which of course is our good friend the oxygen, and 2 hydrogen atoms. And when that collision occurs, we have the direct potential for NH3 competing for a hydrogen atom with water. And what happens is remarkable here. The NH3 succeeds in stealing an H plus from water. Now that's quite a feat, because that hydrogen is bonded quite strongly into that structure of water. But the thing that weakens that hydrogen bond and allows ammonia to steal that hydrogen atom is the fact that the electron delocalization from the hydrogen to the oxygen weakens that HO bond sufficiently so the NH3 can compete and form the NH4 plus the OH minus that creates the basic character of that mixture.